Calculus! Fire up, son! Now, this topic here is not only my absolute favorite topic, but it's also the single most important thing you're going to be doing in maths. It absolutely dominates the maths sphere. So the best thing you can do is get good at it, which actually shouldn't be all that hard because it's an awesome topic. Once you get on top of it, it actually becomes really easy and really enjoyable. So let's get into it. Lesson 1, I'm actually just going to intro you to calculus, and I also want to show you where it first evolved from, and that's learning how to do differentiation by first principles. Alright, let's start off with a history of calculus. Now this isn't in the syllabus, but I found it pretty interesting. It's always nice to know where stuff comes from. So in terms of a history, I want to introduce someone by the name of Sir Isaac Newton from England. Now this is considered to be one of the fathers of calculus. He is probably the single most brilliant mind that will ever grace this earth. The guy was beyond genius, to the point where he was apparently very antisocial. He was that smart, he just couldn't converse with other people. Now, he actually used calculus to prove a lot of his physical properties and laws that he famously discovered. So, as far as we know, he was the first person to use calculus. However, he didn't actually go ahead and publish stuff on it. The first guy to actually publish stuff was a guy by the name of Gottfried Leibniz from Germany. Now, he actually came along and he published a couple papers on calculus. He started to define calculus as we know it today. As it happened, Newton then went and accused Leibniz of plagiarism because he reckoned that the information had gotten to Leibniz and he had caught wind of it and used it. But when they later on did independent studies, it actually went on to show that they got to their own forms of calculus independently. So, as it happens, despite all the fighting which actually divided the English-speaking maths world for decades, turns out we now accredit two fathers of calculus, Newton and Leibniz. Alright, history out the way, let's talk about what calculus has in store for us. So calculus is pretty much going to be divided into two major and opposing processes, and that's going to be differentiation and its partner, which is integration. Now, we are going to spend the next significant period on differentiation. That's where we're going to spend a lot of our focus at the moment. And I've just thrown in a few of my wacky little symbols there. They should look like gibberish, and whether it intimidates you or excites you, either way, all of that's going to make a lot of sense within the next couple lessons. So, let's jump in. Alright, differentiation. What is differentiation? Well, to differentiate is to find the derivative of a curve. Now, what does that mean if you don't know what derivative is? So the derivative is the gradient of the tangent to the curve. Gradient of the tangent. So whenever you hear derivative from now on, just think gradient of the tangent, or the slope of the tangent to the curve at a point. Or in graphical form, you can see there's a curve. The gradient of the tangent will be the slope of that orange line, which is a tangent to the curve at that orange point. So that is what we're going to want to try find out, is the slope of that line at that particular point. And that's what differentiation does. It finds the derivative, which is the slope of the tangent to the curve, or the gradient of the tangent. So, how do we go about doing that? Now, this is where the genius that was Newton or Leibniz or whoever it was, they actually started with this. And what they did is they actually went back to the only thing we know about gradients, and that's our coordinate geometry. We know that our gradient from a couple of years ago, our m, or gradient, is equal to y2 minus y1 over x2 minus x1, the rise over the run sort of thing. Now, I've taken 2 points there. There's the orange point and the black point. We could technically find the gradient between those 2 points using y2 minus y1 over x2 minus x1. And that's what I want to do in order to derive our equation. So let's give those some labels. We'll call the orange point, we'll call it x across and f of x up. Easy enough. Now what we're going to do is we're going to say that the black point is an arbitrary distance across. We're going to call it h across. It could be anything, 1, 2, 100. It's h across. Therefore, that x value of the black point is going to be x plus h. So that should make sense. And the y value, just because of functions, will be f of x plus h. So that leaves us with our 2 points. Our orange point is x, f of x, and our black point is x plus h, f of x plus h. Now let's use those in our formula. We'll call them x1, y1 and x2, y2 respectively. And now we'll sub them into our gradient formula. So we sub them in and we get f of x plus h minus f of x all on x plus h minus x. We tidy up the denominator there. The x minus the x cancels each other. And we're left with f of x plus h minus f of x all on h. Okay, that is the gradient between those 2 points. Now, this is where the genius happens, because in order to find the gradient of the tangent at a single point, so at the moment we found a gradient of a secant, which is between 2 points. We want to find the gradient at a single point. So what we want to do is actually move that black line, or that black dot, a lot closer and closer and closer and closer. So what we're going to do is we're actually going to move that closer and closer and closer and make that h smaller and smaller and smaller. So you can see us sliding that along, closer and closer and closer, so close, and the h gets so small that it pretty much approaches 0. In other words, it's actually going to be right on top. It's the equivalent of 1 point. So we sort of found in the gradient between 2 points, but moving the points so close together that they're the equivalent of 1 point, but still using that formula. And that's the essence of where they get the original differentiation formula from. Okay? And that is this. F dash x, and what f dash x is, it's the symbol for the derivative. We'll go into a bit more in a sec, but that's, if you ever see that, that's the derivative. So the derivative, which is what we want to find, is equal to the limit, which we've just done limits, so that should make sense. The limit as h approaches 0. In other words, as h gets smaller and smaller and smaller and smaller, so small that it basically creates 1 point. So the limit as h approaches 0 of f of x plus h minus f of x all on h. And we derived that from our gradient formula. Now, even if you didn't follow all of that, it's not a big deal because that's not testable. That is just how they derive that equation, derive that formula. The only reason I go through that is it's a lot easier to remember that formula, and it makes a lot more sense if you actually understand where it comes from. So let's explore that formula a little further. That is what we know as our first principles formula, because it was the first principle of differentiation, of calculus. So f dash x, remember I said that's the derivative. They can also phrase that as y dash or dy dx. All of these are 100% interchangeable. If you've got that dash or you've got dy dx, it just means the derivative. Okay, so f dash x equals the limit as h approaches 0, as h gets really, really, really small, so small it basically becomes 0, of f of x plus h minus f of x all on h. Okay, we're going to do a couple examples of that now, but one thing I want you to do throughout first principles, actually anytime you have a formula, but particularly with this one, I want you to use my chopping board. And that means I want you to go out and prepare your ingredients. Prepare your f of x plus h. Make it easier to then sub them in to your recipe. So go do your chopping board on the side and sub them in. Alright, let's try a couple examples. First example. Differentiate f of x equals 5 minus 3x by first principles. Alright, first things first. We write out our formula, which by now you should hopefully be remembering. F dash x equals the limit as h approaches 0 of f of x plus h minus f of x all on h. Remember, the next thing I ask is please do your chopping board on the side. It'll make it a lot easier for you. So, chopping board on the side. F of x equals, well, they told us it was 5 minus 3x. Then to get f of x plus h, we know from functions, just replace wherever there was an x, replace it with x plus h. So we've got 5 minus 3 into x plus h. Do it one step at a time. In the next step, you can go expand it out. That gives us 5 minus 3x minus 3h. And now we're ready to sub that into our formula. So we sub them in. We sub in our f of x. We sub in our f of x plus h. I like to sub them in a bracket, and in the next step we'll go expand it through. That way we won't make any expansion errors with the negatives and that sort of thing. So I'm just nice and cautious when it comes to that, not skipping steps. So in the next step, we can expand it out. 5 minus 3x minus 3h, and now we expand the minus. It's minus 5 plus 3x, and that's all on h. Next line, we tidy that up, so the minus 3x cancels with the plus 3x, the minus 5 cancels with the plus 5, and we're left with minus 3h on h. And as you can see, those h's then just cancel. So the limit as h approaches 0 of minus 3, well, there's not even an h there, so it doesn't matter if h approaches 0. The derivative is simply minus 3. So in other words, the derivative of f of x equals 5 minus 3x is equal to minus 3. The derivative of that is minus 3. And that's how the process works. Let's try another example. Now with this, as you know now, that top left where you see the try it yourself first question mark, pause me here. Give it a go. If that first example made a little bit of sense, give it a go, try it yourself, and then press play and catch up to it, and you'll see me go through it myself. Okay. Second example, differentiate f of x equals x squared plus 2 by first principles. So first things first, exactly like before, write out our formula. Now I want you to say out loud the formula with me now, because it should be starting to sink in. So it's f dash x equals the limit as h approaches 0, as h gets really small, of f of x plus h minus f of x all on h. Should be grained in by now. And what should also be grained in by now is chopping board. Let's do it. F of x is equal to, as we see there, x squared plus 2. F of x plus h is equal to, well, wherever there was an x, replace it with x plus h. So it becomes x plus h all squared plus 2. In the next step, we'll expand that out. And we'll just use our shortcut that we know, where we square the first, twice the product, square the last. If you're not sure of that, go review the lesson on that. So that becomes x squared, so you square the first, plus twice the product, 2 times xh, plus the last squared, which is plus h squared, plus 2. And that's our f of x plus h. Now we're ready to sub them into our recipe or our formula. So, as I said before, sub them in as a whole entity in brackets so that we don't make any negative expansion errors. In the next step, we'll go expand it out. So that becomes x squared plus 2xh plus h squared plus 2, all as is. Then the minus expands, so it becomes minus x squared minus 2, all on h. Now let's tidy that up. Cancel anything you can. The x squared minus x squared goes. The 2, the minus 2 goes. We're left with limit as h approaches 0 of 2xh plus h squared, all on h. Okay. Now, if you get to this situation, you'll find that there's an h as a common factor on the top there. Take that h out, and that'll leave you with h outside of 2x plus h over h. And those h's on the top and bottom now cancel. Because you can't just sub in the h approaches 0 onto the bottom, because you'll get a denominator of 0. This is something we did in limits beforehand. So what we're ultimately trying to do is cancel those h's out. Leaves us with the limit as h approaches 0 of 2x plus h. Now we can sub the h approaches 0, so it's the equivalent of h being 0, and that leaves us with 2x. In other words, the derivative of x squared plus 2 is 2x. And that is first principles. That is how it's done. It's ugly, it's long, it's monotonous, it's boring, all of the above. But if that makes a little bit of sense and you're following that, trust me, you're winning, because this is the worst part of calculus. It's boring and it's outdated. As you'll see, we're going to learn a new method which is super efficient soon. But unfortunately, this is still in the syllabus, and we've still got to go back to our roots, to Newton and Leibniz, and appreciate how they did it initially. So we have to know how to do things by first principles.